Hello everyone, today we're going to be working on fundamental problem 7-33, and this problem is asking us to determine the internal normal force, shear force, and moment at point D of the two-member frame. So this is a two-member frame because, as you guys could see, it is being joined together by this hinge support right here at point B. So this is one side of the member frame, and then this is the other side of the member frame. So that's why it is a two-member frame. So as you guys can see, we have our point D right here where we will be doing that cut to determine the internal normal force, shear force, and moment. So as you guys can see, when we do this cut, we're either going to have to choose to work with the left side or the right side of the frame. So if we were to work with the left side of the frame, we would be dealing with all of this of the frame. So here we have this distributed loading right here and a pin support right here. So we have two unknown reactions right there. So we would be dealing with a concentrated force right here and two unknown reactions. Now, when dealing with the right side, we could deal with it in two type of ways. We could deal with the whole thing. So if we were to deal with the whole thing, we would have a concentrated force of this distributed loading as well, and once again, two unknown reactions. Or what we could do is we could simply just stop this member right here at this hinge support, and that way we would not have to deal with this concentrated force. But since we would stop right here at this hinge support, we know that at the hinge support, we would also have two unknown reactions. But for some reason, it just seems a bit easier for me to work with that. So that's what we're going to do. We're just going to be working with this part of the frame. But to work with that part of the frame, we have to find out the value of those two unknown reactions. So to do that, I'm going to be working first with this side of the frame, and then I'm going to proceed to work with this side of the frame to then be able to determine my internal forces. But before doing that, what I'm going to do is I'm going to find the concentrated forces of these two distributed loadings. So to find this one, I'm going to call this concentrated force F of 1. And since it is a right triangle, as you guys could see, we're going to be having to multiply our force by 1/2 since it is a right triangle and not a uniform loading. So we have 1/2 of our loading, which is of 2.2 kilonewtons per meter. And we could see that it goes on for a span of 3 meters, as we know from this side. So times 3 meters. And with that, our meters would cancel out, giving us just the force. So our concentrated force comes out to being 3.3 kilonewtons. And then for our second distributed loading, we have a force of 2 kilonewtons per meter for a span of 3 meters again. But this is a uniform loading, so we don't have to multiply it by 1/2. So we have 2 kilonewtons per meter. Multiply that by 3 meters once again. Our meters will cancel out, giving us a concentrated force of 6 kilonewtons. Now, as for the locations of these concentrated forces, since this is a right triangle, we do know that a concentrated force for a right triangle will either be 1/3 inwards from the highest loading point or 2/3 inwards from the lowest loading point. So it will be somewhere around here. We said with a value of 3.3 kilonewtons. And since we did say that it is 1/3 this way and 2/3 this way, if we were to include some dimensions, we know then, sorry, we know then that from here to here is 2 meters and from here to here is 1 meter, since we know there is a total distance of 3 meters. And then for the location of this one, we know that since it is a uniform loading, it would just be mid-span, halfway. So right there with a value of 6 kilonewtons. So now that we have that, I'm gonna now proceed to working with this side of the two-member frame to determine one of my reactions. So you would want to draw it out. I already drew it beforehand. So this is my drawing of this part of the two-member frame. Since, like I said, point B is a hinge support, as you guys could see, which is why we have our two unknown reactions. Then at point C, we have a pin support, again, two unknown reactions, and then my concentrated force. So to determine the values of my reactions at my hinge support and not having to deal with the reactions at point C, what I'm going to do is I'm going to be taking the sum of the moments about point C. That way I would be solving for my reactions at my hinge support and not at my pin support. So that's what I'm going to do. So I'm going to be taking the sum of my moments about point C. That means my concentrated force will be creating a moment. It would be creating a positive moment with a force of 6 kilonewtons. And then the distance from my concentrated force to my point C is of 1.5 meters. From there, my B sub Y reaction will not be creating a moment, but my B of X will be creating a moment. Since I assume that it's going to the right, it's going to be creating a clockwise moment, meaning a negative moment. We're trying to determine the force, and then we know that from my hinge support to my point C, there is a span of 3 meters. And we know that all of that has to equal 0. So from here, we would simply just be solving for B of X. So we get 9 kilonewton meters minus 3 B of X. All of this has to equal 0. So we would simply just be solving for B of X, and we end up getting that our reaction B of X is equal to 3 kilonewtons. We get a positive number, meaning that we assumed correctly the direction of our reaction. So we have found the value of one of our unknown reactions. But to solve for B sub Y, as you guys could see, taking the sum of the moments about point C only solve for B of X, but it will not solve for B sub Y. If we were to take the sum of the moments about point B, once again, it will not be creating a moment, so we can't solve for it. And then taking the sum of the forces in the Y direction, once again, both of our vertical forces are unknown, so it would not do anything. So my next step would be then to work with this side of the frame and take the sum of the moments about point A. That way, my reactions at A will not be creating a moment, but my B sub Y will be creating a moment. That way I would be able to solve for it. So the next step would be to draw out that side. I already drew it beforehand. So I'm going to move it closer. So let me just number my steps. So this was our first step. This was my second step. And this is my third step. So as you guys could see, we have my pin support with my two unknown reactions, my concentrated force 1 meter inwards, 2 meters from here. Then we have this whole member with a span of 3 meters, which is given to us because 1.5 and 1.5. And then we have our hinge support. Now, since previously we were able to determine that while dealing with this side of the member frame, my reaction B of X will be going to the right. Since now I'm dealing with this side of the member frame, we know that our reaction then would actually be going in the opposite direction when breaking it apart. So that's why here I drew my reaction B of X going to the left as compared to going to the right for the previous step that I did. So, and then since I assumed that B sub y was going up in this one, although we still don't know if that's correct or not, then that's why I drew B sub y going downwards in this one. Because remember, it has to be the opposite direction of the other side when breaking up uh, my members at that hinge point. So like I said, I'm going to be taking the sum of the moments about point A to solve for my B sub y. So my concentrated force will be creating a moment. Remember, our reactions at A will not be creating a moment, so we're not going to do anything with them. My concentrated force will be creating a clockwise moment, meaning a negative moment, with a force of 3.3 kilonewtons, and then the distance is of 1 meter. From there, we have my reaction B of X, which is going to be creating a This one's going to be creating a counterclockwise moment, so positive moment with a force of 3 kilonewtons. And then we know that from here to here, there is a span of 3 meters. So times 3 meters. And then from there, my reaction B sub y is going downwards, so it will be creating a clockwise moment, meaning a negative moment. We don't know the force, that's what we're trying to determine. And then we know that from here to here, there is a span of 3 meters. And we know that all of that has to equal 0. So simplifying this down, we have negative 3.3 kilonewton meters plus 9 kilonewton meters minus 3 b sub y. All of that has to equal 0. So from there, we would end up getting negative 3 b sub y is equal to 5.7 kilonewtons. Meters. And then from here, we would just simply, sorry, wait, hold on, you guys. Did I do this correctly? This is going downwards. Clockwise moment, negative moment. Yeah. Yeah. Okay, sorry. So negative 5.7 kilonewton meters, we would simply divide both sides by negative 3. So we end up getting that our reaction B sub y is of 1.9 kilonewtons. And since we did end up getting a positive number, that means that we do know that it will be going downwards if we're dealing with the left side of the two-member frame, and going upwards if we're dealing with the right side of the two-member frame. So now that we have this, I can finally now simply just work with this part of the frame to determine my internal forces. So I'm going to be drawing a free body diagram of that. So that's going to be my fourth step. A free body diagram, which is basically just going to be the frame. We have our hinge support right here. And since in a way we're dealing with the left side of the frame, that means that our reactions will be going in the direction of the left side of the frame, so like this. So we know that our reaction B of X will be going to the left with a value of 3 kilonewtons. Our reaction B sub Y will be going downwards with a value of 1.9 kilonewtons. And then we know that our cut is right here because we cut at point D. And we know that from point D to our hinge support, there is a span of 1.5 meters. So I'm going to include that. And then from there, in this free body diagram, you want to include the direction of your shear, normal force, and moment based on sign convention. So since our cut is to the left, we know that our shear force will be going upwards. Our moment will be going clockwise. And then our normal force will be going away from the cut. So to simply solve for our internal forces, what I'm going to do is to solve for my normal force, I'm going to be taking the sum of the forces in the x direction. Here we have our normal force going to the left, so that is a negative force. And then my other horizontal force is going to the left as well, so that's another negative force of 3 kilonewtons. So from here, we would end up getting that our internal normal force has a value of negative 3 kilonewtons. So this is our normal force, our internal normal force. Now to solve for our shear force, I'm going to be taking the sum of our forces in the y direction. So we have our shear force going upwards, so positive. And then from there, we have our other vertical force going downwards. So that's a negative force. So negative force of 1.9 kilonewtons. All of that has to equal 0 since those are our only two vertical forces. So we end up getting that our shear force has a value of 1.9 kilonewtons. So this is our internal shear force. So from there, we would simply just have to solve for our moment. So I'm going to be taking the sum of the moment about the cut. And in this example, it would be at point D. So we know that that has to equal 0. Here, based on our sign convention, our moment is going clockwise. So that is a negative moment. So negative moment. Since we're doing it about the cut or about point D, we know our shear force and normal force will not be creating a moment. Our reaction B of X will also not be creating a moment. The only force that's going to be creating a moment is our reaction B sub Y. It will be creating since it is to the right and going downwards, a clockwise moment as well, with a force of 1.9 kilonewtons and then with a distance of 1.5 meters. So we have another negative moment. Force 1.9 kilonewtons, distance, sorry, 1.5 meters. We know all of that has to equal 0. There we go. So we would simply just be solving for our moment. So we end up getting that our moment has a value of negative 2.85 kilonewton meters. And with that, we are done with our fundamental problem 7-33. Sorry, this is our moment. So once again, what we did is we saw where our cut was going to be. We decided that we were going to be working with the left side of the frame, but I just wanted to deal with this part of the frame. So I had to find my two reactions at the hinge support. So the first thing that I did is I found the concentrated forces of these distributed loading, as you guys could see. From there, I drew this side of the frame to first find my reaction B of X by taking the sum of the moments about point C, giving me a B of X. From there, since I wasn't able to solve for my reaction B sub Y with this side of the frame, I then drew out this side of the frame. And then from there, I took the sum of the moments about point A, and that way I was able to solve for my B sub Y. And then from there, I simply just drew out a free body diagram of this part of the frame, and I included the cut and the direction of my shear force, normal force, and moment based on the sign convention. And I simply just took the sum of the forces in the S direction to solve for the normal force, the sum of the forces in the Y direction to solve for our shear force, and the sum of the moments about the cut to solve for our moment force. Thank you guys so much for watching this video. If you found this video useful, please feel free to give this video a thumbs up, and also feel free to subscribe to our channel if you guys would like to see more videos like this one.